name is Jacob Dayan, and today I'm going to talk about the following slinky for Lab 5 for Physics 2211. So to begin with, the purpose of this experiment is to measure and predict the motion of a stretched slinky being dropped from rest, and to then create a computational model to predict the motion of the object and compare it to our experimental model. The tools for this experiment were GlowScript and tracker video analysis to compare both models. So some of the key concepts we're going to talk about is Newton's second law, first of all, which we can derive from the velocity object formula, and the net forces acting on the system are the gravity, the drag force, and the force of the slinky itself. So first of all, the drag force, which is basically the air resistance, equals the negative of the object's speed squared times its direction. And we also have our gravitational force, which we know is minus mg in the direction of y positive. And we have our slinky force, which turns out to be the tension force of the slinky itself, which I'm going to explain later. Using tracker, the motion of the object falling from rest was able to be measured. The center of mass of the object is indicated by the red dot in each frame as it moves in the negative y direction. The corresponding table and graph show the relationship position versus time, as shown from the slow motion video. Also, the bottom of the slinky remains motionless, as the tension forces is equal and opposite to the gravitational force, just as it was at rest. Therefore, the bottom of the slinky was chosen to analyze this type of motion. The mass in the object was 0.25 kilograms, estimated by the average metal slinky mass, and the initial position of the object is located at 0.031 meters in the x direction and negative 1.85 meters in the y component direction. The amount of time it takes for the slinky to reach the ground is 1.78 seconds, and since the object is being dropped from rest, the initial velocity is 0 meters per second in all components. As the velocity of the object increases, it is proven that there are forces interacting on the object. So to begin our computational model, first we have our initial conditions. We have the mass of the ball, we have the initial position and the initial velocity, and we have our delta t as well. We also put in the magnitude of the acceleration due to gravity, which is 9.8, and we have the unit vector for the positive y-axis, which is pointing up. And we also have the constant for the magnitude of the drag force. So for the first iteration of our computational model, we first apply the momentum principle, and then we update the object's velocity as well as its position. Then we advance the clock by updating the drag using its time intervals. So our second iteration is to control how fast the program runs. First, we calculate the net force. Then we apply the momentum principle, and then we update again the object's velocity and its position. And we run the clock again with continuing with our time interval. And here we have our short results for our GlowScript. As you can see, the green line is slinky, and we can see how it starts falling. So now we're going to compare our computational versus our experimental model based in our results. As you can see, our blue line is our observed motion, and our cyan line, which can we barely see, is our predict position for this slinky. Okay, so the results show that the predicted and the observed values are very similar, except for a few discrepancies once the object started falling. This could be due to the fact that the slinky may have continued forces acting upon itself. It was originally analyzed as the top of the slinky came in contact with the bottom of the slinky, it continued to fall as one, but there could still be tension and other factors contributing to the fall of the slinky. In the future, I will try to analyze both the top and bottom parts of the slinky to see if the velocity changes with contact, or if any additional forces need to be included. Some sources of error could come from human error and mistakes I did when I was calibrating the motion of the slinky with the tracker video analysis to extract the data from the observational model to compare. Overall, this lab indicated how multiple forces can impact the falling object, even if one of those forces is coming from the object itself. So what does it mean? The question for the experiment was, why does the bottom of the slinky stay stationary when it starts falling? So the bottom of the slinky initially remains motionless because the tension force of the slinky, which is basically a large spring, is equal and opposite to the force of gravity, canceling out each other. We can see this when we draw our free body diagram. And once the top of the slinky hits the bottom of the slinky, the forces at play include the force of gravity and the drag force. Therefore, the force of gravity is greater than the drag force, causing the slinky to drop and compress.